Okay, so let's get started. Welcome back, everyone. So in today's lecture, we are going to continue our journey through sorting algorithms. So when we last left off, we were looking at merge sort, and we had just finished looking at the analysis of it. So I'm going to actually rewind a bit and have a look at it again. Right, so here's the diagram of how merge sort works. Right, so in the top half in blue, you have the splitting of the arrays, and then the yellow shows the merging of the sorted arrays into bigger sorted arrays. Okay, so how did we analyze merge sort? We looked at the splitting and the merging. Right, so remember that when we split an array into two roughly equal halves, that's actually just an O1 operation, right? Because all we're doing is calculating the midpoint and then calling the function recursively on the left half and on the right half, right? And if you have n elements in your array, then the total number of splits you have to do is n minus 1, right? So the splitting takes O(n) time, right? But it's the merging that actually takes most of the time, right? So in order to analyze the merging, we have to think about how many levels of recursion do we actually have, right, when we are doing the splitting. Right? Even though we are doing n-1 splits in total, the number of levels of recursion, like if you look at the number of rows here, is actually log base 2n, right? And why is it log base 2n? Because we're halving the size of the array every time. And how many times do we have to halve an array until we have an array of size 1? Well, that's about log base 2n. Okay? So we have log base 2n levels of splitting. That means we're also going to have log base 2n levels of merging, right? And we analyzed merging earlier in the lecture, and we saw that in order to merge two sorted subarrays into a single sorted subarray, that takes about O(n) time, where n is the number of elements in total, right, that we're merging. Right, so if we merge these two arrays of size 1 into an array of size 2, then that takes about 2 steps or 2 comparisons, and same across the entire level. Right, and if we add all of the comparisons up across the entire level, that's going to be n, right? And the same kind of analysis applies to the remaining levels. So to merge these two subarrays into a subarray of size 4, that takes about 4 comparisons, and same for these two. So across this entire level, the merging takes about O(n) time again, and same for the final merging step, right? So for each level of merging, we perform about n comparisons, and there are about log base 2n levels of merging. So the merging takes O of n log n time. Okay, so that's where the n log n comes from. Okay, and this is pretty much what I said before. And in addition, the best case, average case, and worst case time complexities are all n log n. All right, so because merge sort kind of does the same thing regardless of whether the array is sorted or not. Right? It doesn't have anything special to deal with a sorted array or a nearly sorted array. Okay, so that's one way of analyzing it. Another way of analyzing it is to use a method that isn't covered in the course, so isn't in the scope of the course, but is covered in a later course. If you do COMP2521, you might see this, but it's called the master theorem. Right? Sounds interesting. But yeah, here is how it goes. So if Tn is the amount of time taken to sort n elements, right? So n, let's say n is the size of our array. Let Tn be the time taken to sort the array using merge sort. Right? Then we saw earlier that splitting an array into two halves takes constant time, right? And merging two sorted arrays takes n steps, right? If your arrays are size n on 2, right? So this is the formula that we get for the amount of time taken. Right? The time taken to sort n elements is 2 times the time taken to sort an array of size n on 2, right? Because we have two halves and we're merge sorting each of them. So that's 2 times tn on 2 and plus n. So n is the time taken to merge the two sorted subarrays into a single sorted subarray. Right? And if you use the master theorem, then you can use that to show that the time complexity is big O of n log n. Okay? So not required knowledge, but just something interesting and something to look forward to later. Okay, so what are the properties of merge sort? Right, so we saw earlier during the merging demo that merge sort is stable, right? Because every time we compare two items with the same key, we take from the left half of the array, right? And that guarantees stability. Another property is that it's non-adaptive, right? Because during our analysis, we saw that merge sort is n log n regardless of how the array is sorted. Okay, so n log n, best case, average case, worst case. And merge sort is not in place, right? Because when we merge two sorted subarrays into a single subarray, we need to use a temporary array in order to put all the elements in, right? And then we copy the elements back into the original array. So it's not in place. So it uses a temporary array of size up to n, right? And also, in terms of memory usage, merge sort also uses big O of log n stack space, right? Stack meaning the part of memory that contains all the stack frames, right? That's because merge sort is recursive, so there are about log n levels of recursion. So uses up about log n stack space. All right, so that is merge sort on arrays. Now, we're not going to talk about this much, but you can also merge sort linked lists, right? Using a similar idea. So if you start out with an array, then you split it into two roughly equal halves, right? A and B. Then you recursively merge sort each half of the list. And the base case is when you have one element in your list, right? And then after you have the two sorted lists, you then merge them into a single linked list. Right? And the interesting thing about merging linked lists is that you don't actually need a temporary array, right? Because with linked lists, you can just rearrange the pointers and you can get a sorted list without storing anything in a temporary array. Okay, so that is merge sort on linked lists. And it's actually a nice exercise to take two sorted linked lists and merge them into a sorted list. If you're looking for practice on linked lists, that's a nice kind of task. Okay, one more thing about merge sort is that the merge sort that we've been talking about is called top-down merge sort, right? And the reason is that we the merge sort process kind of starts off from the top level problem, right, which is to sort the entire array from low to high, right, and that gets broken down into two smaller subproblems, and then those get broken down into two small subproblems, and so on. So it starts from the top, right, the top level problem, right. There's another variant of merge sort called bottom-up merge sort, which instead of starting from the top, it starts from the bottom, right. So it kind of takes the individual elements of the array, merges those into arrays of size 2, which are sorted, right? And then it takes the arrays of size 2 and merges them into sorted arrays of size 4, and then it takes those, then merges them into bigger and bigger sorted subarrays until the entire array is sorted, right? So it starts from the bottom, right? So bottom in terms of, if you look at this diagram, right? So it starts from this bottom level here. All right, so, and this approach, it's kind of variant of merge sort, is non-recursive, right? So how it works is that it treats the array, so the initial array is not sorted, right? So bottom-up merge sort treats this initial array as containing n sorted arrays of size 1, right? And let me just show you the diagram of this, right? So here's the original array, right? It's not sorted, right? So bottom-up merge sort says, right, we're starting with, in this case, 16 subarrays 16 sorted subarrays of size 1, right? So, obviously if you have a single element, then that's considered to be sorted by default. Right, then the first thing it does is it takes adjacent pairs of elements, right? So AS, OR, that's another pair, TI, that's another pair, and so on, and it merges those into a sorted subarray of size 2, right? So AS gets merged into AS because AS is already sorted, OR gets merged into OR, TI gets merged into IT, NG gets merged into GN, and so on, right? So now that we have sorted subarrays of size 2, we then take those, merge them into sorted subarrays of size 4, as you can see here. So ASOR get merged into AORS, and so on across the entire array. Okay, and this continues. So each time we're going to take 2 sorted subarrays of size M, for example, and then merge those into a sorted subarray of size 2M, right? So each time the size of the sorted runs is getting twice as large until the entire array is sorted at the bottom, okay? So yeah, that's what this is describing. And here's the implementation of merge sort, of bottom-up merge sort, and not all the code is here. See, we're calling the merge function from earlier in the lecture, right? But how does it work? Well, we start off with m equals 1, right? So m is going to be the length of the sorted subarray, right? Initially, the array is not sorted, so we say that there are n subarrays of size 1, right? And after each iteration, we double that value, right? Because every time we are merging 2 sorted subarrays into a bigger sorted subarray, which is twice as long, right? So m times equals 2. And inside this for loop, we have another for loop, which kind of takes the sorted runs and merges them, right? So it starts from the beginning of the array, I equals low, and then this end variable is used just in case the array isn't, in case you don't have the same number of elements at the end, right? So if your array size isn't a power of 2, like 2, 4, 6, 8, then eventually you'll get to some point where, you're trying to merge something of size m, you're trying to merge a run of size n with a run of size less than m, because there aren't as many elements at the end, right? So this variable is used to just calculate that. And then we call the merge function, right, which takes integer I, index I plus m minus 1, so that's the midpoints, and end. Okay. So don't need to worry about this too much, but that's just a different kind of merge sorts. Okay, so that is merge sort. Does anyone have any questions? Yeah.
So if we have a bottom-up version, why what's the advantage of using the recursive?
So if we have a bottom-up merge sort, what is the advantage of using top-down merge sort? That is a good question. So, so I'd say that top-down merge sort is kind of easier to understand, like the logic of it. So, you calculate the midpoint, then you call it recursively, then you merge. Yeah, I don't see why you couldn't use bottom-up merge sort, because bottom-up merge sort is non-recursive. That means it uses one stack space, right? You only need one. You only have a constant number of functions on the stack. So yeah, that's a good question. I'd say bottom-up merge sort is what you'd prefer, yeah, if you had to choose. But yeah, still think the top-down merge sort is easy to understand, easy to implement. Yeah. Any other questions? Yeah.
How would we calculate the time complexity of merge sorting?
How did we calculate the time complexity of merge sort? Are you talking about the top-down version?
Yeah, so like counting the lines.
Counting the lines. So in this analysis, we didn't count explicitly the number of lines, but we saw that, okay, so this is a long function, but we saw that this function here is going to be approximately on because of the number of comparisons that it makes. And if you actually count the number of iterations of the while loops, you'll probably see that in the worst case, the number of iterations of all the while loops combined is going to be n, about n. And same for this for loop, the number of iterations is going to be n because you're copying everything back. So we saw that this merge function was on. Was there... Yeah, and I explained how we get the n log n here. Yeah. Okay, so if that's all, we will go on and have a look at a different divide and conquer sorting algorithm called quicksort. Right, and this sorting algorithm takes a different approach. It's still a divide and conquer algorithm, but it's a little different. And part of the motivation for quicksort is that merge sort kind of does all the work during the merging step, right? It kind of divides the array into two halves in a sort of simple way, maybe you could call it a dumb way, right? Just calculates the midpoint and then recursively merge sorts both halves, right? With quicksort aims to find a more intelligent way of splitting the array, right? And here is how it works. Right, so first of all, if we have an array, we're going to choose an item to be something called the pivot. Right, so choose one item in the array to be a pivot, and there are different methods of selecting the pivot, which we'll talk about in a bit. Then we're going to rearrange the array, and this is called partitioning. So we'll partition the array so that all the elements on the left of the pivot are less than or equal to the pivot, and all the elements on the right of the pivot are greater than or equal to the pivot. And then after that's done, we're going to recursively sort each of the partitions, right? And the nice thing about that is that after we're done, after we've recursively sorted each half, we don't need to do anything else, right? The array is going to be sorted, right? So we don't need to do anything to merge the two arrays back together because the array will already be sorted, right? And here's the kind of diagram showing how quicksort works, right? And these slides are actually a bit updated since the slides that I uploaded on Tuesday. So this is just I just made a few improvements. But here is kind of diagram showing how quicksort works, right? And you can contrast this to how merge sort works, right? With merge sort, right, we start off with two unsorted halves of the array. We recursively merge sort them, and then we merge the two halves back together, right? In quicksort, the recursion actually happens after all the hard work has been done, right? Let me get back to this, right? So we start off by performing the partitioning, right? And what that's going to do is, let's say X is our pivot, right? Then the pivot is going to end up in the middle of the array somewhere. Everything on the left is going to be smaller. Everything on the right is going to be larger, right? But the arrays themselves are not sorted, right? So they're sorted with respect to the pivots, but the arrays themselves, the elements within them, aren't in any order, right? And then we take these two halves of the array and then we quicksort them recursively, right? And then after that, the whole array will be sorted. Okay, so yeah, the big question here is how do we partition the two, or how do we partition an array, right? Because quicksort is recursive, so we don't need to worry about this part, but how does partitioning work? Right, and there are different ways of partitioning an array, but I'll just show you one way of doing it. So how it works is that, first of all, we're going to place the pivots at the beginning of the array, just to get it out of the way. Right? And then we're going to create two indexes, one index on the left side of the array and one index on the right-hand side of the array. Right? So we'll call them index L and R. Right? So L is going to start one index after the pivot. R is going to start at index high. Right? And then until index L and R meet, we're going to advance the left pointer, or the left index, until we find an element that doesn't belong on the left-hand side of the array. So we'll advance the left pointer until the element is greater than the pivot. Right? Then we're going to stop the left pointer. We're going to go to the right pointer and decrement that until we find an element that's less than the pivot. Right? So that element doesn't belong on the right-hand side of the array, it belongs on the left. And after we've done that, we're going to swap them. Right? And we're going to repeat that until L and R meet in the middle. Right, and then we're going to take the pivot and then swap it into the middle of the array. Right, so I'll show you a couple of examples of this. All right, so here's our array, and suppose our pivot is 4. Right, so what we're going to do first is to create our left and right indices. Right, so first, the left index is going to be pointing at 2, the right index is going to be pointing at 5. Then we're going to, until the indices meet, we're going to advance the left index while the element at that index is less than or equal to the pivot. Right, so 2 is less than or equal to 4, so we're going to advance it. Now 7 is not less than or equal to 4, so we stop the left pointer. Right, then we go over to the right pointer, and then we decrement that. Right, while the element is less than or equal to pivot. Right, so 5 is greater than or equal to 4, so we decrement. 2 is not greater than or equal to 4, so we don't do anything. So we stop. And now that we've found these two elements, we swap them. Right, so we swap them. Right, and now we've kind of moved the 2 to the left-hand side of the array where it belongs, and we've also moved the 7 to the right-hand side of the array where it belongs. And now we just repeat the process. So increment left index, so 3 is less than equal to 4, so that's fine. 6 is not less than 4. Meanwhile, we go to the right pointer, right, we decrement that. Now 1 is not greater than 4, so we stop. And we swap the two elements. Right. And now we go over to the left pointer again, we advance that, and now the pointers meet in the middle. Right, so we stop. And now we swap the pivot into the middle of the array. Right. And you need to be a bit careful about which element you swap with. Right. If the indices, so if they met at an element which is less than or equal to the pivot, right, then you swap the pivot with that element, right? But if the index where the two indices met, if that contains an element greater than pivot, then you need to swap the pivot with the element to the left of where the two indices met, right? In this case, that's what we have, right? So the problem is if we swap the 6 with the 4, right, then you end up with the 6 on the left of the 4, right? And that doesn't make sense because 6 is greater than 4, so it shouldn't be on the left, right? So you take the element to the left of where the indices met, and you swap that with the pivot, right? And now the pivot is in the middle, right? Everything on the left of the pivot is less than or equal to it. Everything on the right of the pivot is greater than or equal to it, and we're done, right? And now you would go on and recursively quicksort both halves. Okay, here's another example, a more interesting example where the array is actually sorted. Okay, so we're going to take the leftmost element as the pivot again. So the pivot is 1. We're going to create our left and right indices. Right, and now we're going to take the left index and increment that while the element is less than or equal to the pivot, but this element is not less than or equal to the pivot already, so we stop. Right. Then we go over to the right index. We're going to decrement that while the element is greater than or equal to the pivot. And so that means we decrement it all the way down to 2, and this is where the indices meet. Right, and now we're going to take the pivot and swap it into the middle, right? Except this isn't quite the middle of the array, right? We're swapping kind of the pivot with itself, right? The pivot's going to end up where it started, right? Because everything else in the array is bigger. Right, so now, after we do the swap, we're done. Right, everything on the right of the pivot is greater, and there is actually nothing on the left in this case, right? Because we happen to choose the smallest elements as the pivot. Okay, so as you can see, the choice of pivot really affects how balanced the two partitions are, right? In this case, we chose a pretty good pivot, right? And the pivot ended up in the middle, right? But if you choose an element that's kind of the smallest value or the largest value, then you end up with two really unbalanced partitions, right? So, okay, so that's partitioning. And what is the time complexity of partitioning? Well, it's about O(n), right? And the reason is that the partitioning process performs about n comparisons in total, right? Because each of the elements here is being compared with the pivot, right? And we perform some swaps, but at most that's going to be n on 2 swaps. Okay, and here's the implementation of quicksort, and it's called naive quicksort for a reason, which we'll discuss in a bit. And as you can see here, we're once again quick sorting between low and high, right? And the base case again is if there is only one element in our array or no elements, then we return. Otherwise, we partition our array, right, between low and high. And notice that the partition function returns the index where the pivot ended up, right? And that's because we don't actually know once we select the pivot where it's going to end up, right? So we're going to have to return that so that we know when we recurse on the left and the right halves of the array, where each half starts and ends, right? So we get the pivot index from the partition function, then we recursively quicksort between low and pivot index -1. We recursively quicksort between pivot index +1 and high, and then we're done, right? Cool. So nice thing about this is that there's no merging step after the recursion, right? After we quicksort each half, the array is sorted. Okay, and here's the partition function. Now, right, this looks kind of funny because we have nested while loops, right? But the function is still O(n), right? So let's kind of go through this. So in this partition function, we take index low, so the leftmost elements as our pivot, right? Then we create our two indices, right? The left index and the right index. Then while the indices haven't met in the middle yet, we're going to, so this first inner loop advances the left pointer while the item is less than or equal to the pivot. Right, so while L is less than R and items L is less than or equal to the pivot, we advance the left pointer. And then the second inner loop decrements the right pointer, right, while the element at that pointer is greater than or equal to the pivot. Okay, and now if the pointers have met in the middle, then we break. Otherwise, we swap the two items, and then we go back around and do it again, right? Now, this after this while loop is done, the pointers have met in the middle, and that means we need to swap the pivot into the middle of the array now, right? And this if statement here kind of deals with the case where the pointers have met at an index where the element is greater than the pivot, right? So if that's the case, then we want to swap the pivot with the element to the left, right? So that's just there for that special case. So you need to be careful about what you swap the pivot with. Right, then, yeah, you swap the pivots, which is at index low, with the middle of the array, and then you return L. Right, so that's your pivot index. Okay, so let's analyze quicksort now. Right, now, the best case of quicksort is n log n. Right, and the reason for that is similar to our analysis for merge sort. Right, in the best case, we choose a pivot that belongs roughly in the middle of the array. Right, so we choose a pivot where roughly half the elements are smaller and roughly half the elements are bigger. Right, and that means the pivot is going to end up in the middle of the array after we partition. Right, and in the best case, this kind of happens at every recursive call, right? Every level of the process. Right, and that means we're going to have roughly log base 2n recursive levels, right, in our quicksort. Right, similar to why merge sort is log base 2n. And each level of the recursion is going to require about n comparisons, right? Yeah.
You said log base 2n, but earlier when you were explaining time complexity, didn't you say the base of the log doesn't actually matter?
Yeah, so when we write the time complexity, we drop the base, yeah. So yeah, so here you see that the best case is n log n. Yeah, so this is where the best case of n log n comes from. Okay, so at each level we pick a good pivot so that the pivot ends up in the middle. We have two evenly sized arrays, and we recursively quicksort those, and in each of those we select a good pivot again, and so on. Okay, now in the worst case, right, we end up choosing the lowest or highest value for the pivots, right? And this is kind of what you get, right? So suppose we end up choosing the lowest value for the pivot every time, right? Then after we partition, we're going to get one partition of size 0 because there's nothing on the left, and we're going to get another partition of size n plus 1, which is going to contain everything else in the array, right? And that is going to result in having n recursive levels, right? Because at every level, we're going to have one less elements than before, right? And on the first level is going to require n comparisons, right? The next level is going to require n minus 1 comparisons because there's one less element. The next level is going to require n minus 2 comparisons, and so on. Right, so if you add all of those up, that's your typical arithmetic sum, right? And you end up with about n squared comparisons. So the worst case, quicksort is big O of n squared. Okay, so how about the average case? Right, well, if the array is random, right, so that's what we consider to be the average case, then the chance of actually choosing a bad pivot at every level is going to be pretty low, right? In most cases, you end up choosing a value that belongs somewhere in the middle, right? So, so the bad luck kind of gets minimized. The chance of choosing a bad pivot gets minimized, and it kind of averages out to being n log n. Okay, and we can also show this empirically by generating random sequences and sorting them. In fact, maybe I can do that here. Let's see. So, yeah, I have a naive quicksort program. So let's generate. Let's go with 1 million items because I know that it's going to be pretty fast. So generate 1 million randomly ordered numbers, and we're going to pass that to our quicksort program and time it. And I'm just going to redirect the outputs of the program to dev null, so that because we don't care about the output, we only care about how much time it takes. So if I run the program now, it takes about 0.31 seconds. Yeah. So greater sign means redirect the outputs. So here we're redirecting the output of the program, which is the numbers, the 1, 2, 3, 4, 5, and so on, to dev null. Dev null is just a sinkhole for all your outputs that you don't want. Okay, so it takes about 0.3 seconds, actually, okay, 0.3 seconds, pretty consistently. Right, and this might be surprising because the input is random, right? So you might think, well, why isn't the variance a bit greater? That's because it kind of averages out, or the bad luck and good luck, bad pivot, good pivot. It kind of averages out in the end. If we double the input size, then I claim that the program is going to take a bit longer than twice the amount of time, right? So maybe 0.64 seconds. So we'll see. So actually, okay, takes about 0.59 seconds. So that's interesting. But let me double it again, and maybe this time it'll take more than 1.2 seconds. Okay. well, quicksort is linear, guys. I don't know what to say. So, yeah. So quicksort is pretty fast. It should be n log n, by the way. Maybe if you time, yeah.
So just on this topic, since you kind of so very complicated algorithms.
Yeah.
Do we always do it manually how we've been doing it now, with lines and all that, or is it ever done like empirically where we just give it a really big data set and then run that a few times and then kind of try and understand what the time complexity is by analyzing that instead of by trying to look at the program manually?
So the question was, when you're analyzing complicated algorithms, is it better to analyze it like theoretically by counting lines?
Theoretically versus like empirically, I guess.
Yeah, so yeah, when you're analyzing a complicated algorithm, if you're going to use that algorithm like in the real world, I think best, so if it's really complicated, then I think best would be to actually analyze it empirically. Because that's kind of, you might get an average case which is actually quite fast compared to the theoretical worst case, because maybe the theoretical worst case isn't going to happen very much with real life data. So yeah, I think I would do it empirically. Yeah. Okay, so yeah, the average case of quicksort is n log n. So maybe if you time quicksort again on a different machine, maybe it might actually exhibit that trend. Okay, but let's have a look at the properties. So quicksort is unstable, right, due to the long-range swaps between elements during the partitioning phase. Non-adaptive, that's because on average, right, quicksort is n log n, and sorted input, like if the input is sorted, like it's still not going to be better than n log n, right? In fact, it's going to be worse, and we'll look at that in a bit. And quicksort is in place, right? Because the partitioning process kind of swaps the elements within the array itself. And in terms of memory usage, in the worst case, your stack depth is going to be O(n), right? You're going to use about n stack, n levels of recursion or n stack frames, because in the worst case, you end up with this kind of scenario, right? Meanwhile, on average, your stack depth is going to be O log n, okay? Because you end up with something like this. Okay, so that is the properties. Now, there are some issues that we have to talk about with quicksort, right? And the first one is something that we already kind of saw earlier when we looked at some examples of partitioning, right? If we choose a good pivot, right, then that pivot is going to end up near the middle of our array, and we're going to have two balanced partitions, right? So the ideal pivot is to pick the median value, right? And the worst pivot would be the largest or smallest value in your array. Right? Now, the problem is, well, if you say, well, just choose a good pivot then, right? You don't know whether the pivot you're choosing is a good pivot or not up front, right? And also, the method of choosing, the strategy of choosing the first element as the pivot, the leftmost element as the pivot, is actually not really a good idea in practice. And that's because in the real world, sorted inputs or nearly sorted inputs are actually quite common, right? So existing order is a worst case because when you choose the leftmost elements, you're picking the smallest element as a pivot. Even reverse order is a worst case because you're picking the largest elements as the pivot. And both of these, you'll end up with partitions of size n-1 and 0, so very unbalanced. Yeah.
Yeah, you said in like a practical situation, nearly sorted data sets are quite common. Could you give an example?
I don't have one off the top of my head, but maybe I'll get back to you on that. Yeah, so the question was, nearly sorted inputs are quite common. Is there an example? Not at the moment that I can think of. Okay, and yeah, and because of that, this pivot selection strategy is called quicksort, a naive quicksort, right? Because we're kind of picking a really basic pivot, and that turns out to not be quite good. So to deal with this, we have other methods of selecting a pivot. But the first one is called median of 3 partitioning. And how this works is we actually, instead of picking the leftmost element as the pivot, we look at 3 values in our array, the leftmost elements, the middle elements, and the rightmost elements. And we're going to pick the median out of these 3 as our pivot. Right? So instead of just having one value, we're going to pick between 3 values. Right? And if we do this, then ordered data is no longer going to be a worst case for our partitioning, right? Because if we have ordered data, then the middle value is going to be the median, right? So we're going to end up picking that element as our pivots, right? And so median of 3 makes it less likely that you're going to get a bad partitioning or uneven partitioning. Right. Even though it is still possible, it is possible to generate an input such that median of 3 will always pick a bad pivot. Right. But in the real world data, it's not going to be very likely. Okay, so yeah, so how the median of 3 process works is that you take the leftmost elements, rightmost element, and middle elements, and you sort them such that the median of those elements is on the left, right? And after you've done that, you can call the partition function, and that's going to take the leftmost element as the pivot, which was the median value that you found. All right, so you sort them such that this is true, the median is on the left, and then you partition the array as normal. Okay, so here's an example. So if we have this array and here are our elements, which element is going to be selected as our pivot? Yeah, so it's going to be 5, right? Because the elements that we are considering are 2, 8, and 5. The median of these elements are 5. So yep, we're going to choose 5 as our pivot, and we're going to rearrange these 3 elements such that 5 is on the left, right? And then we're going to partition the array as normal. Okay, so here is the implementation of median of 3 quicksorts, right? So this function here, the quicksort function, is almost identical to naive quicksort, except we call a median of 3 function that rearranges the 3 elements that we mentioned earlier. Right, so this function here, it calculates the midpoints, the middle elements, then it rearranges them so that index low contains the median of those. Yeah.
Yeah, sorry, I just didn't get one thing about it. So basically what you're taking the middlemost value and the low and high value, right?
Yeah.
And then you are rearranging it such that you are putting the median of those three values at the low index,
Yeah.
and then using that as your first pivot.
Yeah.
What's the reason behind the choice of, so on the few slides ago where you're explaining what exactly it is, it says sort it such that A of low plus high divided by 2 is the lowest value. Like, why are you putting the lowest value in the middle and then the highest value there? Like, is there a particular reason for that, or is it just because you're swapping?
That's because of how we're swapping the elements.
Okay.
So we want to put the low index, so we want to put the median value at index low. And in order to find the median of three numbers, you kind of need three comparisons. And we end up just swapping them in such a way that the median ends up on the left.
Okay, so the what ends up in the middle and the high index is coincidentally to like how we're
yeah,
right?
Yeah, so how the other two elements, where those end up don't really matter.
Yeah, so what matters is that in the low index you have your
median.
Okay.
Yeah.
So choosing 3 and moving the median to the left, does it happen every time you recurse through the...
Yes. Yeah, so that happens every time you recurse. Yeah, every time. Okay. Yeah, so that is median of 3 partitioning. Another method of choosing a pivot is to choose it randomly, right? And if you choose your pivot randomly, then there is no input that's going to consistently lead to the worst case performance of O(n)(, right? Because it's random, right? At one point you might pick a bad pivot. In other times you'll pick a decent pivot, right? So it kind of averages out, and with randomized partitioning, you get n log n performance almost all of the time. Okay, so that is randomized partitioning, and here is the implementation of randomized partitioning. So, so we have our base case again. So low is greater than higher return. But before we partition, we select a random element in our array, and we do this by generating a random integer between low and high. Right, so we call this helper function for that. So that generates a random index between low and high. I'm going to choose that element as our pivot and swap it with index low, right? So that when we call the partition function, the pivot that we randomly chose is on the left. Okay, and the rest is as with naive quicksort. Okay, so that is randomized partitioning. And now we need to talk about some possible improvements to quicksort. Yeah.
It's nearly impossible with the random inputs. Does that random pivots? Does that mean the randomized pivots is better than the median one?
So for real life data, these two are probably going to be the same in terms of efficiency, because it's actually quite hard to generate input that median of 3 performs bad on, like performs, has O(n)() performance on. Randomized partitioning, well, it's random, so you're going to get, on average, a decent pivot most of the time. Yeah, so I'd say they're about the same. Okay, so possible improvements to quicksort. So when you have a small array, say size 10 or less, then these recursive, like divide and conquer sorting algorithms, like merge sort and quicksort, they're actually quite slow compared to simple sorting algorithms like insertion sort. Right? And the reason is that these these sorting algorithms are recursive, right? So there's some overhead with calling the function recursively. Right? Every time you call a function recursively, you need to create a stack frame for it, and so on. Right? And the merging and partitioning function actually have some setup required. Right? So if we go to here, right, there's a lot of setup involved in these partition functions and merge functions, and this can add up when you're actually sorting a small array. Right, so for small subarrays, right, the idea is to not sort them using quicksort, but to handle them with a more efficient sorting algorithm such as insertion sort. Right, and insertion sort is sort of the king as far as sorting small arrays. Right, so here is how you would implement that improvement. Right, so in your quicksort function, if the difference between high and low is less than some threshold that you've chosen, then you sort it using insertion sort instead of recursively, doing quicksort. Right, and then you return. So that's one way of implementing it, where every time you encounter a subarray of size less than your threshold, you use insertion sort. Another way of doing it is to defer that until the very end, where if you have a subarray that's small enough in size, then you don't sort it. And after the quicksort process is done, then you call insertion sort on the entire array. Okay, and both of these are roughly equivalent, but I'd say that this second version is a bit better because you're only calling insertion sort once on the entire array. Okay, so that is the insertion sort improvement to quicksort. Now, here's just a little bit on quick sorting linked lists, right? So just like how we can merge sort, yeah.
And you said it's roughly the same when you call insert sort in the end. That's because insert sort is adaptive, right? So when it's near the start and that state, it's going to be significantly faster. Right?
Yeah. Insertion sort is adaptive, which is a plus in this situation. So yeah, just like with a merge sort, we can quick sort linked lists, right? And I might add a diagram for this later, but how would it work? Well, you would pick the first elements of the array as your pivot, right? Or if you want to, you could pick a random element as the pivot, but that's going to be, that's going to add to the cost of finding the pivot. Right, so you can use median of 3 or random pivot if you want, but then you're going to create 2 new empty linked lists, right? And for each element in the original list, if that element is smaller than or equal to the pivot, or smaller than or equal to the pivot, you add it to list A. If it's greater than the pivot, then you add it to list B. Then you recursively sort A and B, right, using the same method. And then, now that you have the pivots, all the elements that are less than or equal to the pivot in a sorted list, and all the elements that are greater than the pivot in another sorted list, you can concatenate them, right? And that will give you the sorted linked list. Yeah.
By adding to A or B, do you mean you're rearranging where the nodes point, or does it mean creating a new node and then copying the value over?
Yeah, so the question was, when you're adding to list A and B, are you rearranging the nodes on the pointers, or are you creating a new node? You can just rearrange the pointers.
I'm assuming that's faster, right?
Yeah.
Because you don't have to have the cost of allocating memory.
Yeah. So that would be faster. Yeah. Okay. So that is quick sorting linked lists. Right, now just a bit more before we're done with this part of our lecture. So let's quickly compare quicksort and merge sort. Right, so with merge sort, we're guaranteed to have an n log n time complexity, right? Because we're splitting the array into roughly 2 equal halves. With quicksort, when we choose a pivot, we don't know where it's going to end up, right? We don't know whether it's a good pivot or a bad pivot. We just run the partition algorithm and we see where it ends up, right? So in quicksort, we're not guaranteed to have an n log n time complexity, right? But it turns out that quicksort is actually faster than merge sort in practice and in general. And the reason is because of how computers are designed, right? And the gist of it is that when computers access memory, it's faster for a program to access memory locations that are close together as opposed to memory locations that are far apart. And merge sort kind of, because it creates a temporary array during the merging step, it kind of has to access two distant memory locations at the same time, right? Meanwhile, quicksort doesn't create any temporary arrays, right? It just needs to access that one array and swap things within it. So you end up with quicksort accessing memory locations that are quite close together. Okay, and yeah, quicksort is more cache friendly, right? And what a cache is so if you don't have a cache, right, then the program has to access RAM, right, in order to perform any operations on arrays. But if you have a cache, then the cache can actually store, some of the memory in RAM closer to the CPU, right, which is faster to access. And because merge sort uses two arrays during the merging process, it's kind of less cache friendly.
Yeah, that's what we asked about how, with what you said about how accessing distant memory, distant points in memory, which means
Yeah.
two arrays to work with, is that slower because of the fact that you can't cache all of it?
Yeah. So yeah, it's less cache friendly merge sort because you need two arrays that both need to be stored in the cache, and maybe they can't both be stored in the cache, which would cause merge sort to be less efficient. On the other hand, merge sort is better at parallelizing, and it's also stable. Right? So if you want a stable sorting algorithm, maybe merge sort is a good choice. And merge sort is better to parallelize than quicksort because when you split the array, you're guaranteed to split the array into two roughly equal halves, right? Whereas with quicksort, when you choose the pivot, you don't know whether you're going to have two equal halves or not. Right, so it's more easy to parallelize. Okay, so that is quicksort versus merge sort, and here's the summary of the two. Right, so notice that they are both big O of n log n on average, but quicksort is big O of n squared in the worst case. Even though if you have a good pivot selection strategy, the chance of this becomes vanishingly small. Okay, merge sort is stable, quicksort is not, and both of these algorithms are not adaptive. So that is our divide and conquer sorting algorithm. So we'll take a 5-minute break, and after the break, we'll move on and look at one other sorting algorithm, which is really cool. So see you then. Okay, so let's get back into it. And in this part of the lecture, we're going to talk about non-comparison based sorting algorithms. All right, so these are sorting algorithms that don't require comparisons between elements. Right, so first we'll talk about what is a comparison-based sorting algorithm. Then we'll talk about the limitations of them, in particular the n log n lower bound. And then we'll look at an interesting non-comparison-based sorting algorithm called radix sort. Okay, so all the sorting algorithms that we've looked at so far have been comparison-based sorts, right? So these sorting algorithms like selection sort, bubble sort, insertion sort, shell sort, merge sort, and quick sort. So these are all comparison-based sorts because they rely on comparisons between whole elements, right, or whole keys. Right? So a kind of analogy of this is if I give you a bunch of rocks and I want you to sort them by weight, right, and I give you a scale, then you can sort them by putting 2 rocks at a time on the scales and comparing them, and eventually you'll be able to sort them all in ascending order of weight, right? Using any of the algorithms that we talked about, like selection sort, bubble sort, quick sort, so on. Right, so these sorting algorithms only rely on comparisons between whole elements. Right? And we can actually show that these algorithms require big omega of n log n comparisons. Right now, a big omega is something that we saw last Thursday, and this is the only time you'll see it ever in the course. But what this means is that these comparison-based sorting algorithms require at least k times n log n comparisons, right, for some constant k. Okay, and what this means is that the best worst case that you can achieve with comparison-based sorting algorithms is big O of n log n, right? And with the simple sorting algorithms like selection sort, bubble sort, and insertion sort, our worst case was big O of n squared. Right? With shell sort, it was kind of big O of n to the power of 3 on 2, or something else depending on your H sequence. But for merge sort and quick sort, we got time complexities of n log n. Right? So, and it turns out that this is the best that you can do for comparison-based sorting algorithms. So let's see why that's the case with a little example. Right, so suppose we have 3 items, right, or 3 numbers. In this case, I'm symbolizing them with these 3 different shapes, circle, square, and triangle. Right? And obviously, if we were only allowed to perform one comparison, then we don't have enough information to sort them, right? Because you can only compare 2 elements and you don't know what the other element is. Right? Now, so obviously one comparison isn't enough, but it turns out that even 2 comparisons are not enough, right? And the question is why? So if we have 3 items, right, then that means there are 6 different ways to order them, right? So 6 different permutations, right? And assuming that all of these items are unique, then that means one of these permutations is in the correct sorted order, right? So one of these is correct, and all of the other ones are not, right? So now we're allowed to do 2 comparisons. So let me perform these 2 comparisons. So I'm going to check, is circle less than square, right? And is square less than triangle? So I perform these 2 comparisons. And based on these comparisons, there are 4 possible results we can get, right? True, 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 false, false, true, and false, false, right? So 4 possible results, but remember that we have 6 possible permutations, right? And we only have 4 possible combinations of results. So that means that for each of these combinations of results, since we have 6 possible permutations, there's going to be at least one of these combinations of results which will be satisfied by more than one of these permutations, right, by the pigeonhole principle. Right, so here is kind of the 4 different possible results you can get, right? If both of the comparisons are true, so if circle is less than square and square is less than triangle, then we know that this is the correct order, right? So there's only one possible permutation here which satisfies both of these comparisons, right? But if circle is less than square and square is not less than triangle, so true, false, then it turns out that there are 2 possible permutations that satisfy these results, right? And since there are 2 possible permutations, we don't know which one is the correct sorted order, right? We don't have enough information yet, right? We would need to compare this triangle and circle in order to tell us which one is the correct order, right? And same for if the first comparison is false and the other one is true. If both comparisons are false, then we only have one possible result. All right, so that means 2 comparisons isn't enough to tell which order is correct. Right, so that means if a sorting algorithm is only allowed to perform 2 comparisons, then it's not going to be able to sort correctly in some cases. Okay, so here is the more mathematical way of looking at it. So if you have 3 items, then there are 3 factorial ways to order them, which is 6. Right? But if we only perform 2 comparisons, then there are only 2 squared combinations of results that we can get. Right? So 4 groups. So at least one group is going to contain more than one permutation, right, as you can see here. So what we actually need is at least 3 comparisons, right? Because this means there are going to be 8 possible combinations of results, right? That's more than enough room for each permutation to sit in its own group. Okay, so in general now, if we have n items, then there are n factorial permutations. If we perform k comparisons, right, then that's going to create 2 to the k possible combinations of true-false results. So if we have n items, then we need k comparisons such that the number of combinations of results, 2 to the k, is greater than or equal to n factorial. Right? So basically, we're trying to solve for k here. We're trying to figure out what is the minimum possible k. Right? So given n items, we have to perform enough comparisons k such that 2 to the k is greater than or equal to n factorial. Now, there's some math here which you don't need to worry about or memorize, but here it is. So if we take the log base 2 of both sides, we get this, right? And simplifying that using the fact that log base 2 of 2 to the k is equal to k, we get this. So this tells us that k has to be greater than or equal to log base 2 of n factorial. Right? And now we use a result from maths called Stirling's approximation. So there's a link here you can go to if you want to learn about that. But turns out that log base 2 of n factorial is equal to this thing, approximately equal to this. So n log base 2 n minus n log base 2 e plus big O of log base 2 n. Right, so that's a lot of terms. But if we remove the lower order terms, which is these 2, then we get a lower bound of n log base 2 n. Right? And of course we ignore the base, so k is big omega of n log n. Right? So this tells us that we need at least n log n comparisons, or k or some constant times n log n comparisons, if we're using a comparison-based sorting algorithm. Right, so another way of putting it is that the theoretical lower bound on worst case execution time is big omega of n log n. Okay, so with comparison-based sorting algorithms, the worst case that we can achieve is n log n. So can we do any better? So the answer is yes, we can if we aren't limited to using comparisons. Right? So if we aren't limited to just comparing two keys, then we can get a time complexity that's better than n log n in the worst case. Right. The downside, of course, is that non-comparison based sorting algorithms, they require some assumptions about the data that we're sorting. Specifically, if we look at radix sort is an example of a non-comparison based sorting algorithm. Radix sort requires us to be able to break up the key into individual symbols, right, such as digits, characters, or bits. Right, so for example, maybe the number 372 needs to be decomposed into its individual digits, like 3, 7, and 2. If we have a string as our key, then that gets broken down into individual characters. So Sydney, for example, SYDNEY. And formally, we decompose our key K into a tuple, right? So where each of these is an individual symbol, right? K1, K2, K3, and so on. And we use M to denote the number of symbols contained in a key, so the length of a key. Okay, so for radix sort to work efficiently, ideally, we want the number of possible symbols to be relatively small, right? So, and that is the case if our keys are numeric or if they're alphabetic, right? So if they're numeric, then we know that with base 10, we only have 10 digits, right? If we're sorting alphabetic keys, then we only have 26 possible letters, so that is small enough for radix sort to work well. Right, and the number of possible symbols is what we call the radix, right? So that's where the name radix sort comes from. And we denote the radix by R, right? So for numeric keys, R would be 10. For alphabetic keys, R would be 26. Okay. And another thing that radix sort requires is that it requires the keys to have the same length. Right? So if the keys have different lengths, which would be quite common in real life, then we would pad each key with a suitable symbol, right? Depending on what kind of key we are sorting. So if we're sorting a numeric key, then for smaller numbers, we would pad them with zeros, right? So if our longest key has 3 digits, then for a number like 15, we would add a 0 at the front. Right, for alphabetic keys, yeah.
Between the two, is there a particular reason that you choose to add numeric ones but do the padding at the start, whereas alphabetic is afterwards?
Yes, so I'm going to get into that. For alphabetic keys, if we have a shorter string, then we would pad them with a blank character at the end. And the reason we want to pad alphabetic, well, firstly, we want to pad numeric keys with 0 at the start, because if we pad them at the end, then let's see. So if we have number 15 and we pad it with a 0 at the end, then 150 is going to be treated as greater than 123, right? Even though the original number was 15. So that wouldn't really work. But for alphabetic strings, we want to pad them with a blank character at the end, because let me try and think of 2 words. So let's think of the word pad, right? So if we have the word pad and the word padding, right, we consider the word pad to be alphabetically less than padding, because padding has, well, pad is a prefix of padding, and yeah. And in the dictionary, pad would be earlier.
So it is due to the nature of due to the nature of the symbols that we're using in the keys, we have to make a decision about how we choose to handle right?
Yeah. Yeah, so based on what kind of key you have to appropriately pad it.
Also, the fact that with numerics,
Yeah.
We are using 0, which is already part of your radix, right?
Yeah.
Whereas for alphabetic, you're using that padding character.
Yeah.
The fact that that's not in the radix, does that make a difference?
So that's a good question too. So question was, with numeric keys, you're padding with a digit which is already in the possible symbols, whereas with alphabetic, you're padding them with a new character, which is a blank character. So with the alphabetic keys, you will end up increasing the radix by 1, but that's fine because it's just 1 extra. Yeah, so it's just a constant, right? Yeah, so it is fine. So instead of I equals 26, you end up with I equals 27. That's just an extra constant. Okay, so how does radix sort actually work now that we have all the details? So first of all, we break the key up into individual symbols, right? And what we do now is we perform a series of stable sorts, right? The first stable sort we perform on Km, which is the last symbol of each key. Right, then we perform a stable sort on Km-1, which is the second last symbol, and so on until we perform a stable sort on the first symbol, and then we're done. Okay, so and each of these sorts has to be stable, otherwise the sorting algorithm doesn't work. Right, so here's an example. Right, so suppose we have these words, right? In order to sort them using radix sort, we perform a stable sort first on the third character, on the last character. Right, so that's going to give us that. Then we perform a stable sort on the second character, right, which is going to give us this. Then we perform a stable sort on the first character, right, and that's going to give us this. Right, and we need these sorts to be stable because if we had an unstable sort, let's consider the last step here. Right, if we perform an unstable sort, then look at these two words. Right, cat and cog have the same first letter C. Right, if the sort was unstable, then we might end up with a cog occurring before cat in the final result, which would not be alphabetically sorted. Right, so we need all the sorts to be stable. Okay, so we need a stable sort in order for each of these intermediate sorts. So what sorting algorithms have we looked at? Right, we've looked at bubble sort, that's stable. Insertion sort, that's stable. Merge sort is also stable, and it's also efficient. So why don't we use merge sort? Right, if you use merge sort, it turns out that you'll be defeating the purpose of using a non-comparison based sorting algorithm, right? Because merge sort is a comparison based sort, right? And we said earlier that if we use a non-comparison based sorting algorithm, we can actually achieve a better time complexity than n log n, right? A better worst case time complexity. So if we decided to use merge sort for each of these sorts, right, our algorithm is going to end up being n log n, right, or worse. So that's kind of defeating the purpose of using radix sort. Right, so in order to perform these stable sorts, we use a special sorting process, and that is to use buckets. Right, so with radix sort, right, we are guaranteed to have a sort of constant number of possible symbols. Right, that's called the radix. Right. So what radix sort does is it actually creates a bucket for each of these symbols. Right, so we initialize R buckets, and if you need a padding character, then that would just add 1 to the number of buckets. Right, so we initialize R buckets, 1 for each symbol, and the idea behind these buckets is that adding anything to the bucket will take a constant amount of time, right, O1 time, to add something to a bucket. Right, and now the radix sort is going to loop from m down to 1. Right, so m is the length of the keys. So we're starting with m because we want to sort by the last character first, right? Last symbol. So during each sort, we're going to first empty all the buckets. So because we're going to be filling them, so at the start of every iteration, we want to empty all the buckets. Right, and now for each key in our array, we're going to take the ith symbol in the key. Right, remember I starts from m, so in the first iteration that's going to be our last symbol. Right, so we're going to take the symbol at index I and add the key to the bucket corresponding to that symbol. Right, and we have another example for this coming up, so don't worry if this confuses you. But after we've stored all the keys into their corresponding buckets, we're going to clear the array. Right, so A is our original array, so we clear that. And now for each bucket in order, so that means if we have an alphabetic key, then we would start from the blank character, then we go to A, then the B, then C bucket, and so on. For each bucket in order, for each key in the bucket in order, we append the key to the array. Okay, so I'm going to go through an example now to clear up any confusions, hopefully. So assume our alphabet is A, B, C. So our radix is 3. Right, so this is because this is a pet example. I don't want to create 26 buckets. So let's suppose this is our alphabet. And we want to sort this array of strings, array of keys. So ABC, CAB, BAA, A, and CA. Right, so first thing you notice is that the keys don't have the same length. So we're going to pad them with blank characters. Right, so for these shorter strings, we're going to pad them with blank characters at the end. And each key contains 3 characters. Right, so M is going to be equal to 3. Okay, so now here is what our algorithm is going to do. Well, first we're going to create one bucket for each symbol. Right, we've got the blank bucket, we've got the A bucket, B, and C bucket. And here is our original array. All right, now in the first iteration, we're going to sort this array by the last character or the last symbol, right, in each key. So that's what we're going to focus on. And now we're going to loop through the array in order and store each key into its corresponding buckets. Right, so for ABC, right, we're going to store that into the C bucket because its last character is C. Right, for CAB, we're going to store that in the B bucket. For BAA, we're going to store that in the A bucket. For A blank blank, we're going to store that in the blank bucket. And for CA blank, we're going to put that in the blank bucket too. After A blank blank. Right. So remember that inserting each key into a bucket is O1 time, right? So the process of storing all the keys into their corresponding buckets is going to be On, right? Now we're going to clear our array, and then for each bucket in order, we're going to store the keys back into the array, right? So for the blank bucket, we're going to store these keys into the array, then we're going to go to the A bucket, then the B bucket, then the C bucket, right? And now we've sorted the array by the last symbol, right, last character, and all of this is done in On time, right? So now that we're done with sorting by the last character, we're going to sort by the second character, right? Now that means we're going to focus on the second character here and store each key into its corresponding bucket again, right? So for A blank blank, we're going to store that in the blank bucket. For CA, we're going to store that in the A bucket. For BAA, store that in the A bucket. Store CAB in the A bucket and store ABC in the B bucket. Right, then we're going to clear the array again and store these keys back into the array. So A blank blank, CA blank, BA blank, BAA, CAB, and ABC. Right, and this bucket is empty. So now we've sorted by the second character. And notice that these sorts are stable, right? And that's because whenever we store a key into a bucket, we're storing them in the same order as they appeared in the original array. And we're storing them back into the array in order as well. Okay, last step is to sort by the first character in each key. So A blank blank, we store in the A bucket. CA blank, we store in the C bucket. B bucket, C bucket, and A bucket. Right, so now we're going to clear our array again and then put the keys back into the array. So A blank blank, ABC, BAA, CA blank, and CAB. Right, so final result is that our array is sorted. Okay, so that is how radical sort works. Right? It's important that you don't use merge sort or comparison-based sort to sort to do these individual sorts. Right? You need to use a special sort which is efficient. Right? Each of the sorts that we did, sorting by the last character, sorting by the second character, sorting by the first character, each of these is ON. Right. And importantly, it doesn't use any comparisons, right? We don't ever compare two keys with each other. We just look at the individual characters within each key. Okay, let me speed through this. Okay. Okay, so what is the time complexity of radical sort then? So here are the variables that are relevant to us. So our array contains n keys, right? And each key contains m symbols. So we're going to take that into account because if you have really long symbols, then the length of the key is actually going to factor in to the efficiency, right? Because you're performing a sort m times, right? And we also have r buckets. Right, so we'll take that into account too. Right now, a single stable sort is going to run in big O of n plus r time. Right, so a single one of those sorts is going to be big O of n plus r, and so I said earlier that it was on, but we're adding in r here because when we're copying the keys back into the array, we need to loop through all the buckets. Right, so in case the number of keys is actually less than the number of buckets, then that's where the R comes in. Right, and the radical sort algorithm, it performs a stable sort m times, right? One for each key, character in each key. Right, so that means the time complexity for radical sort is this. So big O of m times n plus r. Okay, and if r is relatively small, like let's say we're dealing with numeric keys here where r is equal to 10, then that's a pretty small constant, so we can drop that. Right? For alphabetic keys, r would be 26. We can drop that because that's a relatively small constant. Right? So if r is small, then the time complexity is O of m times n. Right. Now, radical sort, that means, right, if you think about comparison-based sorting algorithms, right, the best we can achieve with that is big O of n log n. Right, with radical sort, we have O of n times m. Right, so instead of log n, we have m. Right, so that means radical sort is going to perform better than comparison-based sorting algorithms if m is fairly small, right? That means our keys are short and arrays are large, right? Because if our array is large, right, n is going to get bigger, log n is going to get bigger. But if our keys stay the same size, then m is not going to change, right? M is going to remain constant or the same as if the array was smaller, right? So, radical sort, situations where you want to use radical sort if your keys are short and your arrays are large. Right, and I can actually show this because I've got an implementation of radical sort. Okay, so here I've got a merge sort program for comparison and a radical sort program, and I have a gen program that generates alphabetic keys, right? Just random 8-character keys. Okay. So now I'm going to run merge sort first. So I'm going to generate 1,000,000 keys, and I'm going to redirect it to my merge sort program. Okay, and let's see how long it takes. Right, so about 0.42 seconds consistently. All right, and if we double the input size to 2 million, then it should take a bit longer than twice of this, right? So we would expect maybe about 0.86, 0.87. Let's see how long it takes. So 0.86 seconds, right? And it's pretty consistent. So you can see that it's not exactly doubling in the time taken, but it's doubling and a bit more, right? So kind of indicative of n log n. Now, if we switch over to radical sort, let's go change that to radical sort, and we'll sort 1,000,000 items, right? And let's run it. We can see that it takes only 0.17 seconds, so faster than merge sort. Right, and pretty consistent as well. And if I double the input size, since the length of the keys aren't changing, right? The length of the keys are always 8. I expect that the algorithm will take exactly twice as long, so maybe 0.34, 0.35 seconds. So let's see. Right, so 0.34 seconds, 0.34, 0.34, 0.34, and 0.34. Okay. So if you don't change the length of your keys, but you increase the size of, increase the input size, the time taken will grow at a linear rate. Okay, so that is radical sort. How about the other properties? Right. So first of all, with stability, radical sort is stable. And that's because all the sorts that we perform in the middle are stable, right? That means radical sort itself is going to be stable. How about adaptability? Well, radical sort kind of does the same thing, right? Regardless of how sorted the array is at the start. So radical sort is non-adaptive, right? So it's always going to be O of m times n. And radical sort is not in place, right? Obviously, because during each sort, we need to create the buckets and then store the keys into those buckets temporarily, and then copy them back. Right? So radical sort is not in place, right? And it uses this much additional space, big O of r plus n, right? So r for the buckets and n for the keys themselves. Okay, and that is radical sort. Now, there are many other non-comparison based sorts out there, but radical sort is the one that we'll just be looking at. So there are sorts like bucket sorts. There is also a different kind of radical sort, which is, so MSD here stands for most significant digit, right? The version of radical sort that we went through was called LSD, or least significant digit, because it starts at the least significant symbol. There's also key index counting sort and other sorting algorithms. And you can look at these if you're interested. But otherwise, that is going to be all for sorting algorithms. So yeah, that's it. So we can get out of here about 10 minutes early. Next week, we'll switch up and talk about some other topics, like ADTs. And we'll also look at our first new data structure, which is binary search trees. All right, so we'll see you next week. Have a good week.